Detecting forest layers with AI. To assure sustainable forest management and to protect biodiversity, forest owners and national agencies, like the Swedish Forest Agency, gather and analyze a lot of information. This information can regard tree height, tree species, number of trees, among many other properties. From this information, experts can make judgments on how different forest areas should be managed. For example, certain forest areas are prioritized for protection, while other forests can be felled entirely or in part. So this forest information can be very valuable, but is often gathered by surveyors in smaller forest areas, a procedure that can be costly and requires expertise and effort. To assist with a wider range of tasks dependent on geographical data, the Swedish Mapping Agency has performed a 3D scanning over large parts of Sweden, including Swedish forests. This data is laser scanned by airborne vehicles and produces a 3D point cloud. We are interested in using this forest point cloud to try to estimate some of many forest properties normally surveyed by humans. While there are lots of properties to be explored, we have chosen to look at layering, also known as stratification, to limit the study. In a plantation, trees might have 1 or 2 strata, while more natural forests can develop to the point where no strata can be clearly made out, a so-called fully layered forest. So, for a few forest plots, we have the laser data and we have a measured number of strata. Now we can try methods to accurately count the number of strata from the laser data and later see how well we did. For this, we examined a method by Wilkes and collaborators and a more custom neural network approach. Wilkes and collaborators measures the gap probability of the point cloud. By deriving this distribution, they were able to count the number of strata for an arbitrary forest plot. In contrast, PointNet++ is a geometric neural network that uses max functions to learn patterns in 3D points, independent of order. As we have lots of examples of 1-layered and 2-layered plots, but very few examples of 0-layered or fully layered plots, we employ augmentation to flip, rotate, displace and remove 3D points to create new plots for our network to learn. While Wilkes and collaborators presented great results in Australian forests, their method seemed to perform poorly on Swedish forests, producing low accuracy scores and high errors. PointNet++ saw a general improvement in performance, being able to more accurately classify the number of strata of previously unseen forest plots. We believe that this thesis demonstrates the potential of geometric neural networks to extract properties from complex 3D structures, and hope that our findings can lead to further optimization in the gathering of information about forests.